Welcome to part 3 of this forming tutorial. In this section we'll define a material behaviour and assign that to the blank. We'll have to assign a section behaviour to the shell elements of the blank. We'll have to define surfaces on each of the instances, and we'll have to define interactions such as friction. Finally, we'll define steps, and in order to make those steps work we'll have to define loads, boundary conditions and amplitudes. Once we've done all that, we should be able to get the simulation to run. Notice I've changed the names of the parts and instances for the top and bottom tool, and that's because those previous names were too long and they would have produced an error when I tried to run the simulation. So the first thing we'll do is create a material behaviour. So we'll call this rubber because we're going to give it a very low modulus in order to make the simulation run quickly. We'll first define a density. We'll give it a density of 1000 kilograms per meter cubed, and then we go to mechanical behaviour, elasticity, and we'll define a simple elastic behaviour with a Young's modulus of 1 million and a Poisson's ratio of 0.3. Next we can define a section behaviour. So we'll call it a shell section, and we'll choose shell homogeneous, and we'll give it a thickness of 0.5 millimeter. And we'll choose the rubber material behaviour that we've just defined. Now we need to assign the section to the blank, so we press assign section, and then we're going to create set2 down here. So we press done, okay, and we can see that it's region set2, okay. And now we can see that there's another set that's been created called set2 within the blank part, and that is also visible down here inside the blank instance. Now we can create surfaces so that the simulation will be able to simulate contact. To do that, we need to highlight the instances one at a time. So open the instances and let's choose the bottom part and hide all the other parts. Double click on surface, call this surf die, choose mesh, then continue, and select the part, and then we've got to decide which side the surface is on. So if you zoom in, you can see that this is on the brown side. We can do the same thing for each of the different instances in the simulation. You'll notice that I define surfaces on both the upper and lower side of both the top blank holder and the blank. It'll become obvious why I've done that as we go through the tutorial. Now we can define a surface interaction property and also the interactions. So let's minimize the sets and the surfaces, and we can see the interaction properties down here. So we're going to define friction interaction. So it's a contact interaction, mechanical tangential behaviour, penalty method, and we'll define friction coefficient of 0.3. Now there's a very simple way to define all the interactions, so we'll call this int all, and we'll choose general contact explicit, continue, we'll choose the friction property, and we'll choose all with self. That means that we don't have to define selected surface pairs. Just press OK. Now we can define boundary conditions for the initial step on each of the rigid tools. We'll select each one and we'll apply an Ancastra boundary condition to each reference point. We can now create 3 different steps. The first step will be a gravity step. After that, we'll apply a pressure step, during which we'll apply a pressure to the upper surface of the top blank holder. And then finally, we'll introduce a punch move step. So let's define a gravity step. Call it grav. And this is going to be a dynamic explicit step. Okay. And we're going to give it a very short time period so that it doesn't slow the simulation down. So we'll give it 0.001 seconds. That's the amount of time that it'll take to apply the gravity to the blank. And we need to create an amplitude. We'll call it amp grav. And choose tabular, continue. So we'll put 0, 0, and then 0.0011. Okay. And then we need to apply a load in that gravity step. So we'll call it load grav. And when we choose gravity, okay, and we have to make it act in the right direction. So it's 0, 0, and then minus 9.81 meters per second in the Z direction. And we'll choose the amp grav amplitude function. Okay, now we can apply a pressure step. Again, it's going to be dynamic explicit, and we're going to give it again a very short time period so it doesn't slow the simulation down. And we need to apply the load during that step. So first of all, create another amplitude called pressure, and we'll do the same thing as last time. 0, 0, 0.001 to 1. That means that the load is going to increase linearly during that time step. And finally, we can introduce a punch move step, call it punch, dynamic explicit, and we'll give it a short time period, because at this point we just want to make the simulation work. Instead of applying a load, we need to apply a displacement. And once again, we'll need an amplitude. So let's create an amplitude called move. And again, tabular. So 0, 0, 0.01, and 1. Okay. And then we're going to create a boundary condition called move. And we'll choose displacement rotation, and we'll apply it to the right part, which is going to be the top rigid body tool, which is the punch. And then we've got to decide how we want to move it. So we'll put everything as 0 first of all, and we'll choose the move step, but actually we want to move it down by minus 0.0, we'll give it 1 centimeter for this initial trial. Okay, now we're almost ready to run the simulation, but we need to have a look at the boundary condition manager first of all. So go here, click on this button, and you can see the boundary conditions applied to each of the instances in the simulation. At the moment, we've got some contradictory boundary conditions, because you'll remember that we applied a Ancastre boundary condition to each of the parts, but then later on we're asking the parts to move. So we need to adjust these boundary conditions, and we can do that by looking at each instance in turn. So first of all, the bottom blank holder should be fixed throughout the simulation. So the fixed condition is created in the initial time step, and then it's propagated throughout the rest of the simulation, so that's fine. The top blank holder should also be fixed in the initial time step and also during the gravity step. But when we apply the pressure, we want the top blank holder to be able to move downwards so that it can transmit the pressure to the top surface of the blank. So we can deactivate that Ancastre boundary condition in the pressure step. So we just deactivate it, and you can see now that it's inactive for the remainder of the simulation. But we do want to constrain the upper blank holder so that it doesn't slide around laterally during the forming simulation. To do that, let's dismiss this boundary condition manager and create a new boundary condition and apply it during the pressure step. We'll call it lateral. and we'll choose the right part, so it's going to be the top blank holder, and we'll make sure that the displacement is 0 in the X and Y directions. We'll leave the Z direction undefined, and we'll also constrain it so it doesn't rotate around any of the axes, and we can leave the amplitude as instantaneous. We can now check that new boundary condition using the boundary condition manager, and you can see that it's been created in this pressure step. Moving downwards then, we can see that the die should remain fixed throughout the simulation, and we ask the punch to move down during the punch step, so that means that we need to deactivate the Ancastra boundary condition for the punch during that time step, like so. We're now ready to try and run the simulation. So go to File and then check the work directory that you're using. So here I'm using the temporary directory, which is fine for now. And then go down to the bottom, double click on job, so we're going to create a job. We'll call it job 1, continue, OK, and then right click on job 1 to submit it. OK. If everything's gone well, then the job should run, and eventually it should complete after a few minutes. So right click on it and then click on results, and you should be able to have a look at the result. So you can see here that everything looks okay. The job's run and there's clearly a contact between the punch and the blank, and it's trying to push the blank down into the female tool, like so. We could easily start playing around with the parameters of the simulation, for example increasing the punch distance. But we've now achieved our main goal, which is to create a fully functional simulation. From this simulation we can create an input file and then start editing that input file to make the simulation work with a textile model rather than a simple elastic rubber sheet. So in the next part of the tutorial I'll show you how to create and edit an input file.